So let's do another example, which tries to clarify concepts that we've talked about for properties of discrete time Fourier series. This problem statement lets us take a few moments to try to absorb what the statement really is. So you're given periodic signal x of n, and the information that's given to you about the periodic signal is these 4 points. So the first thing is that the signal is periodic. Of course, it's periodic with a period of capital N equals 8 samples. So that's the first information that's given to us. The second information that's given to us is that if I sum the signal over one period, that that signal is going to, that sum is going to be equal to 2. Similarly, if I do this sum, which might be a little bit twisted looking, but we're going to see it's related to Fourier series decomposition. This sum is going to turn out to be equal to 1. And interesting, the last interesting point is that among all signals, all periodic signals, and that satisfy the conditions 1, 2, and 3, among all signals that satisfy this condition, x of n has the minimum power per, per period, right? So that's the information that's given to us. Given this information, we're required to determine what the signal x of n is, right? So really, there's a one-on-one mapping between the signal in the time domain, and which is periodic, and the Fourier series coefficients. If we can determine the Fourier series coefficients for this signal, that would be enough to determine what the time domain signal is. Now, since the signal is periodic, since n equals 8, so how many coefficients do we need to determine? How many Fourier series, unique Fourier series coefficients is this going to have? Of course, there's going to be 8 of those. So we need to determine 8 coefficients. And of course, those are A0, A1, all the way up to A7. So these are the Fourier series, 8 Fourier series coefficients. If we can determine these 8 Fourier series coefficients, we'd also be able to determine the time domain signal. Now, in order to determine these Fourier series coefficients, the first thing I look at is the constraint number 2, or the condition number 2, or the information in point number 2, and try to see if this has anything to do with the Fourier series representation. And a little bit of thought would actually reveal that this is related to the DC component, the A naught coefficient, if you will. Because A naught, if you recall, is just simply going to be equal to 1 upon n. That's the definition. And this summation can go from anywhere to anywhere as long as it's within one period. So therefore, so summation from n equals 0 to 7 x of n, and then there's e raised to power j 2 pi k, but then k is 0, so that's just 1, and therefore this is the definition of a naught. But since we know from the information that's given to us that this thing here is equal to 2, and of course this thing here is 8, so we can easily conclude from this that A naught is going to be, for this time domain signal, is going to be equal to 1 upon 8 times 2, which is just simply equal to 1 upon 4. So that's the first thing that we can determine. So let me write this here. So A naught equals 1 by 4. So that's something we know. We've been able to figure out. What about the condition number 3? So this is from 1. This is from 1. What about from 2? Sorry. What about from condition number 3? Is that related to anything to do with the Fourier series decomposition or Fourier series coefficient? Of course, it is. In particular, so let me write it out. I know that. So this is summation from n equals 0 to 7, j raised to power n, x of n is actually equal to, let me just write j as e raised to power j pi by 2. So that's j here, and raised to power n would just simply be multiplied by n here. So this is x of n. And you see, I mean, we're getting close to what the Fourier series, the synthesis or the analysis equation is. So this is equivalent to n equals 0 to 7, and this is e raised to power j. So this is pi by 2. I just want to write it as k times some integer k times 2 pi divided by n, where a capital N is equal to 4. So this is 2 pi by 8. Remember, capital N is equal to 8. And I just need to have an integer here. I just need to have an integer here so that when I multiply that integer with 2 pi by 8, I am going to get pi by 2. And it's easy to see that that integer turns out to be equal to 2. And then this is x of n. And then clearly, I see that what I have over here is, so let me just, right? So what I have over here is A2, right? So what I have over here is A2, and I know that this equation from condition number 2, condition number 3 is equal to 1, and from there I can easily conclude that A2 times 8 is equal to 1, and therefore A2 must be equal to 1 by 8, right? So another thing I've been able to determine is this: for the Fourier series coefficient A2 sub 2 is going to be equal to 1 upon 8. Now, what about the other ones? So we're left with 6 more. So we've only been able to determine 2 of those. We're left with 6 more, and that's where the condition number 4 comes in. Now, the condition number 4 says that among all signals that satisfy conditions 1, 2, 3. In other words, what that really means is among all those signals, periodic signals of period 8, which have a naught equals, 1 by 4, and which have A2 equals 1 by 8, amongst all those signals, this signal that we're trying to determine has the minimum power per period. And that's where Parsifal's relation can come in, because Parsifal's relationship says that so Parsifal's relationship, if you recall, it says the power per period. So the power per period is equal to the summation over all the absolute squares over the all Fourier series coefficients. And therefore, this is a sum of A0 squared plus A1 squared plus absolute of A1 squared plus absolute of A2 squared all the way up to A absolute of A7 squared. And we know for a fact that this class of signals that we're looking at would have A0 equals 1 by 4 and A2 equals 1 by 8 in order for me to have the signal which has the minimum power. With the minimum power, all other coefficients should be 0, because the absolute score, the minimum value absolute squared it can take is 0. It cannot be negative. So for which implies that for minimum power, all coefficients except the ones that were already determined, so A0 and A2 are zeros. And when I say all coefficients, I obviously mean that k equals either 1. I'm not talking about minus infinity to plus infinity over only one period. So this is 3, 4, 5, 6, and 7. And so therefore, based on the analysis equation, or based on the synthesis equation, I can just say that x of n is just equal to summation over k equals 0 to n minus 1 a sub k e raised to power j k times 2 pi by n, which is just pi by 4 times n. And just if I just plug in what a naught is, and if I just plug in what a2 is, so therefore this is just simply equal to 1 upon 4 plus 1 by 8, and this is times j raised to power n. I could write it as j raised to power n, or e raised to power j pi by 2n. And that completes my solution. That's the xfn that we're looking for.